Okay, well now let's turn to our problem of the day, the step potential. Here, 1 second. Here's the step potential problem. In the step potential, the potential energy is 0 for x less than 0, but it's equal to a constant value for x greater than 0. Okay? That is, it looks like this. 0 for x less than 0, and u0 for x greater than 0. And there's a sharp step at x equals 0. All right? And we'd like to find the wave function everywhere and find how the wave function depends on the energy. All right? And as we do this, it's really helpful to think about a classical analog of this. All right? You'll have to give me a second to draw this. This should work. Shouldn't be too bad. Okay. So let's imagine a situation where we have a ramp that goes steeply down and then has some sort of ramp up, which will represent our potential step. Okay? So this is the height of the ramp. All right. And now, just to make contact with our drawing above, x equals 0 would be here. And then the first part of this ramp, that's just to give our ball or particle some kinetic energy. So imagine a situation where our particle is a ball which starts on the hill at this point, okay? So it has some energy, E. And notice that here, E is greater than U. And at some moment in time, we let go of the ball and allow it to evolve forward in time. Well, what will happen? Well, obviously the ball will roll down the hill, gaining kinetic energy as it moves down the ramp. All right? How much kinetic energy will it gain? Well, if there's no friction, then the kinetic energy will just be the total energy minus the potential energy, like so. Then when it meets the other wall, or the other ramp, the ball will roll up the ramp, turning kinetic energy back into potential energy. And you can see that because E is greater than U0, that the kinetic energy of the particle will never fall to 0 here. It will go all the way up to the top of the ramp, and then it will still have kinetic energy, and so it will continue moving to the right. Okay? So in this case, E greater than U0, in the classical analog, the ball always climbs the ramp and continues to the right. That is, the ball is transmitted through this barrier. Okay? But that's good. But there's a second case we should investigate. Here, let me try and draw that. Actually, I'm going to be lazy here, and I'm simply going to copy my drawing. Oops. And paste it down here. Yeah. There we are. And let me erase a few things so that I can redraw this. The second case will be the case where the ball starts with an energy that's lower than the height of the ramp. Like so. It starts at a point lower than the height of the ramp, so that its total energy is lower than U0. Now at every point, its kinetic energy is still equal to E minus U0, but you can see that as the ball rolls down the ramp and then starts to roll up the other ramp here at x equals 0, it's going to meet a point here where the kinetic energy will fall to 0. All right? And at that point, well, it's going to turn around. This point is called the classical turning point. All right? So when the ball reaches this point, the kinetic energy goes to 0, but there is still a force acting on the ball, pushing it to the left, and so it will roll back down the hill in the other direction. So this is the second case, where the energy of the ball is less than the height of the potential barrier. And in that case, ball is always reflective and never enters the region x greater than 0, or wherever the turning point is. Okay? I guess I shouldn't say greater than 0. In this case, it never enters the forbidden region. Okay, well, that's the classical picture, all right? Now, we'd like to see what happens when we use quantum mechanics, all right? And that's what we're going to do next. And you might think that the same logic will hold. If the energy of the ball, of the particle, is larger than the potential step, then it should be transmitted, because there'll be no point where its kinetic energy falls to 0. On the other hand, if the energy is less than the potential energy step, it should always be reflected, since it can't ever be found in a region where its kinetic energy is less than 0. Okay? And that, that has something going for it. But you might think of another example that will give you some pause. Imagine when light hits a kind of a barrier. Imagine light hitting a piece of transparent material, like a pane of glass. Maybe that's like a kind of a potential barrier for the light. In any event, what happens when the wave meets that piece of glass? Well, in that case, it's partially reflected and partially transmitted. So waves seem to exhibit a different kind of behavior that isn't available to particles in classical mechanics. And so that gives us the thought that maybe we'll see something like that when we consider this problem. Since, we know we have to be able to describe our particles using wave functions. In any event, let's see what we find. So we're going to take a look at this problem, but I think we'll start a new short video to begin our discussion.